This is a review for exam number 3 for process dynamics and control. We have this link here that shows the topics that we're going to be covering for this exam. We have Laplace transforms, transfer functions, state space, second order model, second order plus dead time, and then we also simulated the transfer function, state space, and ODE. We have stability analysis, cascade control, and then feed forward control. So at that link, there's additional information that you can use as you fill out your note sheet. I'm going to have a transform table, a Laplace transform table that's going to be available for you for the exam, so you don't need to write these down on your note sheet. I do recommend Routh array and second order graphical fitting, especially for underdamped systems, and other information that you'll find on those topics. Okay, so fill up your note sheet. I think that's a good part of the review. And then when you come into this practice exam, see how well you can do. And I'll go through the solutions here for the different problems, but try it on your own, see how well you can do just with your note sheet. Okay, here is the first problem. We have two inputs. The very first one is U1 and the second one is U2, and I have U1 coming in and U2 to another transfer function. This first one's going to be 1 over s plus 2, and then the second one is going to be s e to the minus s divided by 2s plus 1, so you have a delay of 1, and then we're going to have these two are going to come together. We'll just add those responses, and then this is going to be y. So we have those transfer functions, we have the input signals that are there graphically. The first question is what is the expression for U1 and U2? So U1, we can find those on our Laplace tables. Okay, so I'm going to go back up to those, just to the Laplace table, and we have a step unit, a unit step here. Okay, and that's capital S. You don't want to confuse that with a lowercase s that's in the Laplace domain. That's just a step input that goes from 0 to 1, and that's going to be 1 over s in the Laplace domain. And then we also have that starting at 1 second into it, so we need to come down here to our delay. So if you have it delayed by a certain amount t naught, then that just means that you multiply by e to the minus t naught s. So for that very first one that we have, let's come back to it, we have u1 of s is going to be 1 over s times e to the minus s. So we have our delay of 1 there. And then our second one, which is u2, okay, let's go back to our Laplace table. Okay, here it is, and we're just going to come up here to the ramp. Okay, with a slope of 1. If it's a slope of a, then it'd be a over s squared. Okay, so let's come back down here. That's just going to be 1 over s squared e to the minus 2s. So it's going to start just a little bit later. Okay, so there are expressions for u1 and u2. And actually, we don't have a slope here of 1. We see that this slope, it goes over by 4 and up by 3. So just one correction here. This is going to be 0.75 for the slope. Okay, let's go on to the next one. We want to derive an expression for y of t. So here is y of s, and we can calculate that just by, we have two transfer functions, two signals in parallel. So I'm just going to name this one y1 of s and y2 of s. And so we know that y1 of s is going to be equal to 1 over s plus 2 times our input, which is going to be 1 over s e to the minus s. And then we have y2, which is going to be s times e to the minus s, 2s plus 1. Multiply that by my input. Okay, and then I add these two together. So now y of s is going to be equal to y1 of s plus y2 of s. Okay, let's keep going with this. We'll go ahead and just combine those two. So y of s equals 1 over s plus 2. Okay, and I'll put the 1 over s over here. E to the minus s. And then we'll combine these two. You have two exponentials there. And so we're going to combine those, but also this one is going to cancel out the squared here. And so let's just combine these two. We'll have 0.75 divided by s times 2s plus 1, and then e to the minus 3s. Okay, so we have our two transfer functions here, and let's go ahead and do the inverse Laplace of these to get it back to y of t. So I need to go find these two. I can leave off the time delay until the very end. So let's go and find those in our Laplace table. So here's something that looks familiar. The first one isn't quite in this form, but let me go and just take a screen grab of this, and then we'll use that over here. Okay, so there's our inverse Laplace. We're going to go from this form back to this form right here. And you'll see that it needs to be in a time constant form. We need to have the tau right there. So I'm just going to divide this by 0.5, or by 2 on the numerator and denominator. So that's going to come up with 0.5, and then I'll have 0.5 s plus 1. Okay, just divided the numerator and denominator by 2. Okay, now I have it in this form. 0.5 can go out front, and then I'm going to transform it, this piece, into the y1 of t. Okay, so that's going to be 0.5 times 1 minus e to the minus t over 0.5, and that's going to be 0.5 1 minus e to the minus 2t. Then I want to put in the time delay to that. So to put in this time delay, wherever you see time, you just substitute that with time minus the time delay, and then you multiply the whole function by the step input that starts at the time delay. So with time delay, just find any of the times that we have. Okay, it's going to be 0.5, 1 minus e to the minus 2 times t minus 1. So I'm going to replace any times with t minus the time delay. And then I have the s of t minus 1. And so that just means this is going to start at time 1, go from 0 to 1. That's this function right here. And then this function right here, graphically, that's going to look something like, let's see, t minus 1, that's going to start right here and go up to a value of 0.5, and it's going to get there in a time constant of 0.5. So we'll have 1, 2, 3, and so 0.5, it's going to be 63%. Oh, sorry, 63% of the way there. So it's going to look something like that. Okay, so we've got our first one. Now we multiplied it by this step function. If you didn't do that, you'd have this thing go down, but because we have this 0 right here, okay, it says that it's going to be 0 beforehand, and then it's going to come up to the new steady state value with an exponential decay. Okay, let's do our second one now. It's going to be very similar to the first. Okay, so here was y1 right here, and let's do y2 as well. Okay, very similar. We just have 0.75, 1 minus e to the minus t divided by 2. Okay, and then when I apply the time delay, 1 minus e to the minus, and then this is going to be t minus 3 divided by 2, and then s of t minus 3. Okay, this is going to come up to a value of 0.75, and it's going to have a time constant of 2, and it's going to start at, let's see, this is going to be 1, 2, 3. It's going to start here, and it's going to come up to 0.75. So eventually come up to that level right there, but it's going to get 63% of the way there in 2 time constants. So it's going to be about 63% of the way there. It's going to look kind of like that. Okay, so I'm going to add these two together, and that's going to give me my final response. So y equals y1 plus y2. So I'm just going to add those together, and so if I added those together, it would look something 2, 3, 4, 5. Something that would come up quickly to 0.5, and then we're going to go up to 1.25, eventually starting at 3, and then that's going to come up kind of like that. Okay, so I just sketched it. If you plot it out, this would be the solution right here. You can see the green line, or actually the yellow line, that is y1. Okay, now that's a blue line. And then you see the purple line, and that is y2. And then adding those two together, you get the combined response. So this is going to be y right here. Okay, so that's the very first problem. We had some input signals, u1 and u2. We had two transfer functions that were in parallel, and those were added together. We were able to find the step and the ramp, and those were both in the Laplace table to come up with expressions for u1 and u2. And then we multiplied those by our transfer functions to get y1 and y2, and then did an inverse Laplace on those, added those signals together, and we came up with what the final response would be if we were computing y of t. Okay, so that's problem exercise number 1. Let's go down to exercise number 2 now. We have, in this case, we're going to have a transfer function for our process that is, I'll just write it here, it's going to be 1 over 5s squared plus 6s plus 1. Okay, so if we give this a step input, it's going to have a gain of 1. It's going to come up kind of like this. It's a overdamped system. Okay, and then we also have a PI controller. This is going to be our PI controller, and this one, the transfer function for a PI controller, is going to be KC times 1 plus 1 over tau IS. Okay, and if we just look at our, I'll derive that later, how we came up with that. And then we're going to have a feedback control system, okay, with a set point, and also our response. Okay, so in this case, we have tau I for our controller. Let's just say that equals 2. And we want to find the range of values, Kc, for which the system stays stable. So we have our closed loop response here, but we need to come up with the range of Kc values that we can use for tuning that are going to keep the system stable. So just to derive this first one for the PI controller, if you recall, you have U equals U bias plus, and then it's Kc times the error. This is in the time domain. Kc divided by tau I times the integral of the error. So if you have a PI controller only, it's U minus U bias is going to be the deviation variable, okay, and then that's going to be U of S, and then we have Kc times the error of S. Okay, I'm just converting each of these terms into a little Laplace domain, and then I have E of S divided by S. Okay, so I just factor out, this is going to be the error, and that's going to be U. And so if I just take this, I have U of S divided by the error equals Kc times 1 plus 1 over tau I times S. Okay, so I have this transfer function I derived for a PI controller. I just put that in there, with tau I equals 2. So let's go ahead and derive the closed loop response. We have y of s divided by y set point of s, and we need to come up with this closed loop transfer function. So if we do some just some block diagram algebra here, we have y of s equals, and I'll just call this the process transfer function, and I'll just call this PI transfer function. Okay, so we're going to have GP times PI, okay, and that's going to be times the error. But we also know that the error is going to be equal to the set point minus the y value that's fed back. Okay, this is also y of s here, and I have a plus here and a minus there. I compare the two, and that becomes my error. And so if I just plug this into here, then I come up with y of s equals GP PI times y set point minus y. And then if I collect y onto the other side, then I have y of s times 1 plus GP PI equals GP PI times y set point of s, and then that comes up with just rearrange this a little bit more. I have GP pi divided by 1 plus GP pi. Okay, so there's my closed loop transfer function, and I'm just going to use the ones that I had up there in the different blocks, plug those in, and then we'll just look at the denominator of our transfer function to look at stability of our system. Okay, so let's do that. We have y of s over y set point of s. That's going to be equal to, okay, so this is kc, and then I'm just going to multiply this out just a little bit, just so it's a little easier to work with. Tau I s plus 1 divided by tau I s. Okay, 1 divided by 5s squared plus 6s plus 1. And then I'm going to have 1 plus that same thing. So I'm just copying it down. Okay, and then I can multiply the numerator and the denominator by tau is times the 5s squared plus 6s plus 1. And so if I do that, I get it into this form. Okay, so let me just do that. Y set point of s. Okay, so it'll be kc times tau I s plus 1. Okay, and then I'll have in my denominator tau I s. Make that just a little bit neater. Okay. Okay, and then I'll multiply that by 5s squared plus 6s plus 1. And then we'll add kc times tau I s plus 1. Okay, so here it is. I've almost got it. I just need to get it into, expand the polynomial a little bit, and then we'll get it into a form that that we can analyze, where we can analyze the roots of this thing. Okay, so now I have kc, and I'll just plug in the 2 for the tau I now, 2s plus 1, and then we'll have 10s cubed plus 12s squared plus 2s plus 2kc s plus kc. So I've just expanded this polynomial and put it into that form. And then we want to look at, there's a couple different ways to do the stability analysis. We're going to use the Routh array here. So let's go ahead and let's come up. Let's see, here is the Routh array method. Right here we take this polynomial and then we look at the leading left edge here and make sure all of those are positive. So let's just get this, I'm just going to grab this and we'll do the analysis over here on the other page. Okay, so there's our polynomial, and we just need to fit it into this form. And so I'm just going to take an is going to be equal to 10. That's my very first one right here. And then 12 is going to be the one that goes right underneath it. And then we have 2 plus 2kc. It goes right here. I just factored out the s. It's that whole term right there. And then I'm going to have right here, I'll have kc. Okay, now we have these 4 terms right here. what we need to do is start computing down what B1, B2, C1 would be. So let's go ahead and use just those formulas there. B1 is just going to be AN minus 1 times AN minus 2 minus AN times AN minus 3. Okay, so AN, let's go ahead and compute this. We have, okay, we got to be a little bit careful here or I'm going to mess it up. Okay, AN minus 1 is the 12. Okay, it's going to be 12 times AN minus 2, which is going to be 2 times 2kc, and then minus AN, which is 10, times AN minus 3, which is going to be kc, and then I divide that by AN minus 1, which is going to be equal to 12. Okay, and then to get my B2, that one's just going to be 0 because these on the right of it are 0. If they're not there, it's just going to be 0. So I'm just going to have zeros, 0 for B2. And then for C1, let's see, C1 is going to be B1. Okay, let's see, that is B1 times AN minus 3. Okay, so that's going to be KC. Okay, this actually is just going to work out to KC because the AN, the B1 is going to be in the numerator and the denominator, so that's just going to factor out. This one's going to be 0, so it's just going to be left with that one right there. So I just have KC right down here. Okay, so for each of this, and then the rest of them beyond that are going to be 0. So each of these in the leading left edge, in order for it to be stable, those have to be greater than 0. So the very first condition we have is just KC has got to be greater than 0. Okay, and that came from this one. Let's look at this one now. Okay, so we have 12. Let's see, I'll just multiply this out. We have 24 plus 24 kc minus 10 kc divided by 12, and that has to be greater than 0. Okay, so that is going to be 14 kc plus 24 divided by 12 is greater than 0. Alright, and the 12 doesn't matter, you can multiply that out, and so KC has got to be greater than negative 24 over 14. But this is a lower number than the one that we got already. So we always take the more restrictive one. So it says that this is our stability limit. We just have KC is greater than 0. We can just ignore this one because it's less restrictive. So there's our stability limit. So one of the things I'd like to just show you is an alternate way of doing this with a root locus plot. We're just going to calculate those poles. Here is a root locus plot, and we're going to start right here. Any of them that are marked with X's, those are your poles when KC is equal to 0. And then as it gets positive, it's going to go this way, and then it's at a certain point it's going to have oscillations. Okay, when you have imaginary, okay, these are imaginary roots of our denominator. And but let's look at an interactive plot of this, because there's actually a really nice feature in MATLAB that'll do an interactive root locus plot for you. So you can select this, and you can see there's your gain. And then as I go this way, you can see At this point, with a gain of 0.113 for my controller, that's when I'm going to start to have some oscillations or overshoot. So you can see how much overshoot there in terms of the percent. Let's say you want to get to 20% overshoot, then you'd have a gain of 1.42, and you see the damping coefficient as well. You can also see the pull that's computed. Okay, so these are going to be symmetric. These two are going to come together at the same point at 0.113, and then you can see this one travel up in a symmetric way to the other one. You have another one over here that is going to meet this 0 and basically end at that 0. Okay, so none of these show instability for Kc greater than 0. So that was our, if we had Kc less than 0, then we would go over onto this right hand side of the plane, and that would mean it was unstable. Okay, so just a second verification of this. This is with a root locus plot showing the same thing that the Routh array method gave us. Okay, let's go on to the next one. This is the final one. We have this PI controller has this following closed loop response, and we want to be able to characterize this. It's kind of similar to the last problem, but now we just have this response, and we want to try to fit it to a second order underdamped system. And so we're just going to use a graphical fitting method to be able to come up with our parameters for the second order system. And a second order system is going to be, this one is going to be Kp divided by tau squared. I'll just put this as K so it doesn't confuse us which K it is. Okay, and then tau squared S squared plus 2 zeta tau S plus 1 e to the minus theta ps. Okay, so we want to fit this response to that, the second order form, and in order to do this, we're going to just first start with the gain. So we have here our delta U. Okay, that's going to be our delta. This is our set point, and that equals 1. And then we see that the response, this is our Y, that's going to level out at a value of 1. This is a PI controller. So we also have that the delta Y is going to be equal to 1 as well. And so our gain for this system is going to be delta Y over delta Y set point, and that equals 1 over 1. So that equals 1. So for this equation, we'll just put a 1 there. Okay, the next thing that we can come up with is the something like the damping coefficient. And in order to do that, we're going to go to, let's go back up, okay, to our note sheet. And these were our notes on fitting a second order response following these steps. We already calculated our gain. Now we want to calculate the damping factor from the overshoot or decay ratio. So the overshoot is going to be this B divided by A. You could also use a decay ratio, which would be C divided by B. So let's come down here. We've got this zeta value right here, and I'll just grab this one so we can see the formula. Okay, and then we'll come back down. Okay, I'll just paste this in here. There's our zeta formula. And so we need to first of all get our overshoot. Okay, so this was going to be B, that's going to be 0.5, and then our A is 1.0, and so our overshoot is going to be the B divided by A, which is 0.5. And so if I plug this in right here, the natural log of 0.5, that's negative 0.69, and then if I square that, that's going to be 0.48, and then I'll also have 0.48 here as well, and then I'll just plug this in and then come up with zeta is going to be 0.215. Okay, there's my damping factor, and you know, this should be less than 1 for anything that oscillates. For an underdamped system, you should have zeta between 0 and 1, and if it's equal to 1, it's a critically damped, and if it's greater than 1, then it's going to be an overdamped system. Okay, let's go on to the next one now. We got to pick out something else that we can use to calculate our tau value. So let's come up to our note sheet. I went one too far. Okay, so we've got a couple options here. We could use, let's say we have everything we need. We could use the period, the length of time for an oscillation from peak to peak. We could also use the peak time, okay, or the rise time. I'm just going to use the period, and I'm going to rearrange that to just get my tau value. So just put tau of s on the left and the period and all the other coefficients on the right. So let's just grab this one. Okay, and then come back to our sheet here, and I'll paste that here. Okay, so we need the period, the amount of time between the peaks. And so here's the 2 peaks. You don't use this one down here. It's the full cycle of the oscillation. And so if we come down here, you just got to kind of estimate it graphically. But this is about 14 seconds. Okay, so if we plug that in, we also had our zeta. That's why we calculate tau later. So we have 1 minus zeta squared. This part right here is going to be about 0.95. Okay, and then we take the square root of that, and it's going to be, you know, everything right here is going to be 0.977. And then with the period there of 14, then this is going to be about 2.176. Okay, maybe too many significant figures there for a graphical method. But that's going to be equal to seconds there. Okay, on the tau value. Okay, so there we have it. We have our tau and our zeta values. And then what about the theta p? So this system right here, it doesn't look like there's any theta p because it starts right away when the step starts. Now the step would be e to the minus 5s, okay, over s. That would be the equation for the step, but the response to that step has no delay. So this one, in this one, the theta p is going to be equal to 0. Okay, for our next part of this, let's just do one more thing. Let's put this into state space form. So here we have a second order system, and we want to get this into a state space form. And so we have this system right here. We don't have any time delay. That theta p is going to go to 0, so that term is going to go to 1. So let's just fit this one into a state space form. We have 1, okay, divided by tau squared s squared plus 2 zeta tau s plus 1. Okay, and that is equal to y of s over y set point of s. And I'm just going to multiply this out on both sides. We're going to do an inverse Laplace. We don't need to find this transfer function in our, we don't need to find that in our Laplace table because we are going to just convert it back to a differential equation, and then that will go back into our state space form. So if you recall, our state space form is going to be x dot, okay, that's dx dt equals ax plus bu, y equals, and then cx plus du. And because it's a second order system, we're going to have two states there. So I'm just going to write it out in a little bit more detail. dx1 dt, dx2 dt. And then we're going to have four different coefficients here. I'm just going to put big circles to fill those in. Those are not zeros. Those are just blank spots there that we're going to fill in. And then we're going to have x1 and x2 plus, and then we'll have two blanks here times our u value. Okay, and then we're going to have our output y. And I'll put two blanks here. And just one blank right here times our u value. Okay, so we just need to fill in the values for all these circles based on our second order system, and what we'll do is just translate this back into a differential equation. So this is going to go back into a form that's y of s times tau squared s squared plus 2 zeta tau s plus 1 equals y set point of s. So this is going to be our u value, and then I'm going to translate this back into the differential form, tau squared, and then this is going to be the second derivative of y plus 2 zeta tau times the first derivative of y plus y equals, and then I'll just say this is going to be equal to u. Okay, so with a second order system, I just need to define these two states, and so let's just say that x1 equals y, and then let's define our second state to be the derivative of y. Okay, and that's also equal to the derivative of x1, and then our derivative of x2 is going to be the second derivative of y. Okay, and that's going to be equal to the second derivative of x1 as well. So, okay, so fitting it back into a state space form, then we just need to, we have one of our first equations, which is this one right here, okay, which is going to be dx1 dt equals x2, and then we need to get the second one from our differential equation that we just derived from our transfer function. So let's go ahead and just put in tau squared, and then dy dt squared is just going to be dx2 dt. We can only have one differential in each equation, so for this next term, the 2 zeta tau for the dy dt, we could either use it's equal to x2, or we could say it's equal to dx1 dt. But let's use x2 there instead, because we don't want a second differential in it. And then plus x1 equals u. So I'll just rearrange this one just to get it into the semi-explicit form with dx d2 dt just on one side, and I'll have minus 1 over tau squared x1, and I guess I have a minus there, 2 zeta tau divided by tau squared, and that's going to be times x2, and then plus 1 over tau squared times u. So I have these two equations right here, and I'm just going to fit those into the state space form. Okay, so this very first one is going to be a 0, and then I'll have a 1 here. And then my next two are going to be minus 1 over tau squared minus 2 zeta over tau. And then here I have a 0. I don't have any u's in my first expression. And then 1 over tau squared. Okay, and then I got to plug it into these other two. And so I'm going to use just this first equation right here to define y. So y equals x2. It's just going to be a 0, 1, and then a 0. Okay, so I've converted this back into state space form. And I could plug in the tau value and the zeta value and come up with my matrices. This is going to be matrix A. This is going to be matrix B, matrix C, and then matrix D. So I guess the question is, why would we want to get it back into state space form versus Laplace transforms? And I guess the answer to that is that these are equivalent systems. There's a lot of things we can do with a state space form. For example, we can look at the eigenvalues of the A matrix, and it tells whether the system is going to be stable. Okay, we can also, this is in the time domain, so we don't even need to do anything in the Laplace domain. It's a very convenient form that allows things like model predictive controllers or other things you can do with the linear time invariant systems. In this case, it's just a linear state space form. Okay, so this was the final one. Let's just review what we've covered so far at this point. This was exercise 3, where we had a graphical second order fit and then converted that to the state space form. I'm going to go page up here, and this was our closed loop response. We were trying to determine the stability limits for KC for this system with a PI controller. And then this one was basically a graphical determination of the inputs. And then we had our transfer functions, and we were calculating our response y. So just coming back here, good strategy for this exam is review all of this material. Make sure you can do problems such as this. You're not going to get hung up on the conceptual things. The numbers themselves, the actual calculations are minor in comparison to showing your work, and then if you make a minor math error, that won't be much of an issue. But just make sure you've gone through each of these. You feel comfortable working in the Laplace domain with state space, with second order systems, and doing stability analysis. We only had one assignment on cascade and feed forward control. And so I'd say don't worry about those as much, but just know that they exist. If you have a feed forward control, you're going to take your standard PID equation, okay, and the integral of, okay, so this would be a PI, and then if you added a feed forward element to it, I'll just do the D as well here. Okay, and that's going to be minus Kc times tau D, and then you have the derivative of your measurement. And then if you're going to add a feed forward, you're just adding a feed forward element. Most times it's just a gain, and then times your disturbance. Okay, and then if you have a cascade controller, that is, you're trying to control your disturbance directly by making an inner loop. Okay, where this is your outer loop, your set point, and here's your primary controller, like a PID controller, and then that gives a set point to another controller. And this is going to be your inner loop. I'll just put 2 there. That's your secondary controller. This is your inner transfer function, like a flow control or pressure control. There's a feedback control there. And then you have your second. So that's your inner process transfer function, your outer process transfer function. And then this one feeds back here. So cascade control is you're basically sending a set point to an inner controller, and then you want to make sure you tune this to be faster than the outer controller, that you're able to follow the set point, or you can lead to some instability issues. So that's basically what I wanted you to know about cascade and feed forward controls. Those are just additions or enhancements beyond the regular feedback control systems that we've studied so far.